Hello, everybody. We are going to start. I'm Marc. I'll be giving today's lecture, which is about algorithms for the integration of ODE. Let me just first do a warning. This is a very wide topic. I mean, integration of ODE is in fact a field of research that's still ongoing, and people are doing papers on this, and it's very, very wide. So I'll give a very narrow perspective on the subject because I have 2 hours, so I can't pretend to cover all the things. So basically, I will focus on 3 kind of methods to integrate ODEs, which are the most basic ones. So I'll start. I'll start with the most basic. I'll start with some previous concepts on what a ordinary differential equation is and so on. And then I'll start with I really don't know what's going on. Okay. I'll start with the very basic one, which is Euler method. It's the way you start integrating all this. And then the rest of the talk, I'll present the Euler method. And then the next section is going to be ways to improve Euler method. So I'll take 3 approaches, which are the well-known Runge-Kutta multilinear step and the not so well-known Taylor method. So I'll take these 3 ways to improve Euler method. And then for the ones who know at least a little bit on integration of ODEs, and particularly the people coming from partial differential equations, you'll know that there are explicit methods and implicit methods. I'll be mentioning implicit methods, but only mentioning them. I won't talk deeply about implicit methods. So then I have this little section here, which is a compendium of phenomenon that make things go wrong. I mean, phenomenon that happened in reality that make the methods I'm going to present fail in some way. And some remarks on that things that can happen and hopefully ways to prevent them. And the last section, it's a little bit of clickbait. I'm sorry for that. It's about a phenomenon that I mean cannot be avoided in general. So and since this phenomenon cannot be avoided, we can't predict the weather, and this phenomenon, by the way, is chaos. So I'll enter into that. So let's start with, I said, some previous concepts, which are about what a differential equation is. And just to fix some notation, to me, an ordinary differential equation is an equation of, okay, this shape, x dot equal to some vector field that depend on t, which is the independent variable, and x, which is the dependent variable, which is in fact a function. And that's the quantity. This function is the quantity we want to know. So if f depends on f depends on t explicitly, we'll say that the system is non-autonomous, and if not, we'll say the system is autonomous. So f is the vector field, and x is the unknown function, and the whole thing is what we want to know. Let me say that in the first instance, this has as many solutions as you want. I mean, if you have x dot equal to 0, all the constant functions are solution of this differential equation. So in principle, we need to fix one variable. We need to fix a initial condition, which is this xt0 equal to x naught here. So when I have a pair of ODE plus initial condition, this is called a Cauchy problem. And this is, in fact, what we want to solve, because with a computer, you cannot solve a problem with infinitely many solutions. You want to do something that gives you numbers. Okay. So our task is learn how to solve Cauchy problems. And let me say some things. I said that the solution is unique, and in fact, it exists with a little bit of requirements on the function and on the vector field. And that's requirements are minimal in the sense that you need continuous with respect to two variables and Lipschitz with respect to the second variable of the vector field. So with that ingredient, you already have uniqueness of solution. But in reality, when we do models and applications, the usual thing is that this F is maybe smooth or analytic. Okay, that's I mean the models primarily are good in terms of regularity. So notice that if I integrate with respect to the time, the Cauchy problem, I get this integral here, which is like some sort of the weak formulation of the problem. And it is, I mean, solve this weak solution is equivalent to the ordinary differential equation. So we'll have a couple of different ways to see the same problem. And more notation to the solution that at initial time t0 passes through the value x naught and evaluated at time t. This has a name which is called flow of the problem, of the Cauchy problem. So whenever I say flow, you can think about of this application, this map. Okay. In principle, if f is good, the flow is good, meaning that the flow inherits the regularity of the function. So if the function is derivable, the flow is derivable. And if the function is analytic, the flow is analytic. So it is a standard also to compute the derivatives of the flow with respect to initial conditions. As I said, if the vector field is derivable, I have that. And this verifies, is a matrix, is a Jacobian matrix, and verifies a set of linear differential equations, which are called variational equations of first order, or first order variational equations. So, and essentially, this does not come from nothing. This comes from deriving with respect to initial conditions, the original equation. And then people with some background on analysis that prove that this works and can be done. So, and usually, if you notice, it is an equation that depends on the flow. So typically, this is integrated together with the original equation. Everything together, and you make a large equation with dimension n plus n squared. So n is the dimension of the vector field, if you want, and then the n squared is the extra equations you need to compute the Jacobian function of the flow. Okay, and this is quite relevant, especially when you're doing some sort of dynamics, because this is useful, for instance, to program a Newton method to compute a, I don't know, a periodic orbit, for instance. Then that's relevant also for to know the stability of such orbit, and then you compute also Lyapunov exponents. And there are many applications with first order variational equations and higher order. I mean, you can also expand the flow, I mean, up to any desired order. Okay, so that's just a little bit of jargon. Let's start with the first method to solve ordinary differential equations of the afternoon, and that's no one else than Euler's method, which has his own section, not because it's the best, but because it's the worst. So let's start with Euler method, which is, I mean, it is very simple to understand. We have an initial condition here, and then we want to predict the next step of the flow, if you want, or the next step of the solution, or the solution evaluated at some time t1, which is t0 plus some h, and h is going to be a small number. H is going to be the step for all this lecture. So in any method, h is a step, which is a small number. So what Euler said? So Euler said x1, so the next point of the solution is x0 plus h times the vector field. Now remember that the equation is x dot equal to fx. So this guy here, the vector field, is indeed the derivative of the solution by construction, or by definition, if you want. So this is a linear approximation. This is a linear approximation of the solution at developed, if you want, around x naught. So you got something like this. If this is x naught, this is the prediction that Euler method is giving. And then you keep going. Once you have x1, you replace here x0 by x1 and get and t0 by t1 and get x2, x3, x4, x5. And you have something like this. Xi plus 1 is xi plus this guy here, which is the derivative. So you keep going, x1, x2, x3, and so on. So the idea of, I mean, why this works is because of this. I mean, this is, if you want, numerical differentiation of the solution with time step x, the left-hand side part, and then this is an approximation which says, I mean, the first derivative, numerical derivative, will coincide with the vector field, which is given. I mean, this is a data from the problem. And here h, if you want, is, sorry, this should be t2 minus t0. So I mean, to make work the formula for the numerical derivative. So what we produce with a method to compute to solve differential equations is in fact a sequence of points, ti xi, a sequence of points that somehow will approximate the solution, the curve of the Cauchy problem. So this is what we produce. Let's move on. I'm gonna think now that this sequence of points is obtained by applying the Euler method, which is this simplest method we just presented. And then we can care about how much I'm wrong. I mean, how the order behaves. And then by a simple, calculus rules, and Taylor expanding, you can see that in fact this error behaves like the square, the square of the step size. So we say that Euler method is of order 1 because the error is of order 2. And that will be important because we are going to generalize this concept of order to any method. And hopefully we will find something better than this. And this is our goal here. So another observation, and this is to pose some jargon, is that this order, this is trivial, by the way, but this order, when you divide it by h and make h go to 0, this quotient goes to 0. And this is the least thing we could expect from a method that computes the solution of an ODE, because the error goes to 0 if the step goes to 0. So that's something you need. But this has a name. If this happens, the method is called consistent. Okay, this is just jargon. Now it is trivial, but at some point we will require this. So let's move on. I have a test equation for this lecture. I'm gonna use it a couple of times, and I'll be integrating more interesting things. But here we have an equation which I know the solution because it is almost trivial. It is this one. So this is x dot x squared plus 2t minus t to the fourth. The solution of this equation is t squared. So it's a parabola, trivial. So I can take advantage of that to check how Euler method is performing. So I just done a numerical experiment, and I started at this initial condition, x is equal to 0, and iterated 500 times the Euler method with a step size 10 to the minus 3. And this is what I get. This is, by the way, the logarithm, the tail logarithm of the error. So when you see a minus 6 here, you have to think about 10 to the minus 6. This is a standard way to display error. So what we see here is that close to 0, the error behaves as expected, as the local error formula is telling me, which is 10 to the minus 3 squared, so 10 to the minus 6. This is a minus 6. So I'm looking just at the exponents. But then as I go on and keep computing more terms and keep the time going, I'm going to losing digits of precision. This is due to 2 things. First of all, is that this kind of formulas for local error happen or hold if h is small enough. That's typical situation in maths. Something is small enough. How much? I don't know. Small enough. So that's one thing. And the other thing is that as I'm doing approximations. So I start with the initial condition which has, if you want, error 0. But then as I keep going, x1, x2, x3, x4, I'm just approximating things. So I have some error that is propagated through the old integration. So this makes 2 things. This makes me lose digits as I carry on. And this is a problem that most of the all of the integrators have, because we're in a computer, we work with a finite precision. So at least we have some error that's propagated through operations. But I mean, some other methods are better than this because we are losing a lot of precision here. We start with 6 digits and then end up with 3 digits only. So let's go on. I'm gonna integrate a little more complicated problem, which is the Kepler problem, which is maybe the first model you do when doing something close to celestial mechanics. That's the basic model for celestial mechanics. And this is an ODE, which is 4-dimensional and autonomous. And it models the motion of a test particle about a massive body. Test particle means an asteroid, and a spacecraft, or maybe a planet orbiting around the sun. So basically what this model does is assume that the test particle mass do not affect, I mean, in terms of gravity, the big mass. So we have a massive particle and a test particle. I mean, this system is in fact very, very simple. I mean, it can be understood like with a pencil. You don't need probably ODE solvers for this. And it's integrable. So it means that it means many things, but the solutions which are bounded are the conics. Well, the solutions which are bounded are circles and elliptics, and the ones that are not are hyperbolas. And well, the curve you get cutting a cone with a plane. So, however, there are here a couple of conserved quantities, in fact more, but we'll care about, first of all, the Hamiltonian of this system. So the system is Hamiltonian, just some information. And then we have this angular momentum, which is conserved. Now, if the angular momentum is conserved, I can use the angular momentum to check on how good I'm solving the equation. I can use it as a proxy of the error I'm doing. So this is what I'm going to do. I'm going to solve this problem with an Euler method, and then look for the conservation of angular momentum. And I have a figure which is rather similar than the one I showed before. Here I'm putting the time, and notice that the time is not, I mean, is half. Is half a unit of time. So it's a very small time. And then I'm seeing the same kind of behavior that I start with 6 digits, which is what I should expect. And then I'm going up to 3 digits. So I'm losing 3 digits in the way. And this is, by the way, this is the log 10 of the error, or the drift of the angular momentum. So I'm putting I'm fixing the first value of the angular momentum at t equal to 0, and then computing the angular momentum at each time and making this abstraction, and this is what gives me the error. So this is in fact bad news. So some of these errors I can do a little or almost nothing about, because they are errors I'm doing because I'm iterating a map. So there is some accumulation. But the fact that I don't know if h, the step, is small enough, I can do something about. I mean, if I use the information the equation is giving me, I can adjust the step size and start with 10 to the minus 3, and then make it shorter if I need something, if something weird is happening. Because this, I used an initial condition which lies in an ellipse with some eccentricity, 0.1. So an ellipse which is something like this, kind of exaggerated. I mean, this has not eccentricity 0.1. So what happens is that if I'm following this curve here, I can do the step size quite large because it doesn't change much. But once I'm here, I cannot, use the same step size because the linear approximation is much worse here. So this kind of phenomena can be controlled if I'm able to estimate the error I'm doing, the real error, not the one that the formula is telling me, not the orders, but the number itself. So this is this can be done in a number of ways. I mean, any idea here is valid, but kind of the basic idea is that if I only knew the right solution, I could estimate the error I'm doing. Of course, I do not know the right solution. If not, I wouldn't be using a solver for the ODE. So to compare, we need somehow to compare with something which is given maybe by a numerical method, or usually by a numerical method, but I know that's better. So here, since I have nothing more available than the Euler method, I'm going to use the Euler method, but instead of doing one step of size h, I'm going to do two steps of size size h divided by 2. So half the step. And then I'm going to compare the two quantities. Now, in principle, if h is smaller, half, then the approximation is better. So I'm going to use this second two steps prediction to compare. And then if you go to the Taylor expansion and so on, you'll see that this behaves. I mean, if you subtract the two predictions, this is the behavior. Some constant, this is constant that depends on the problem, h squared plus some higher order terms in h. So the point is, I have to fix the tolerance. I have to set the accuracy I want to solve the problem. That's a usual thing I have to do with any solution, or with any method. So I fix epsilon, and then I'm going to check that the error divided by h is small enough. And if it is not small enough, I'm going to decrease my step size. Okay? And this is, if this condition happens, this is a quantity, epsilon over r, which is smaller than 1. So I'm in fact multiplying h for something smaller than 1, I have something which is smaller. And then this 0.9 could be a 0.85. I mean, it's heuristic, and it's considered a, let's say, security term to make sure you're in fact reducing the things enough. So if this happens, I reduce the step size. And doing this, I'm using this algorithm, which is the same Euler method, but looking for the step size. And I do the same experiment. And then I check again the conservation of the angular momentum. And it's not spectacular, but I have better performance in the same situation. I only lose a couple of digits. Sorry, 1 digit. So step size control is important. And we'll see later that It is very important. I mean, because one could think that, okay, who cares? I do a very, very small step size and I'm okay with it. So that could be some idea. But that's a very bad idea. Because as I said, every time you do an operation, you do some error because of the operation. I mean, not because the method is of order 2 or 3 or 5, because you're doing an operation with floating point arithmetics. And these kind of errors accumulate along the integration, and at the end it will end up killing the method. I mean, the prediction will be useless. So you have to avoid doing many steps. So essentially, you want to do an optimal step size, small enough to have the accuracy you want, but large enough to avoid time-consuming programs and also propagation of error. So the step size has to be optimal. Okay, that's some more jargon. This is something I said before. We can generalize this notion of that, or the Euler method has order 1 to this definition. If the local error is of order HP plus 1, we'll say that the method has order P. And then we'll say that the method is consistent if the order tends to 0. The local error tends to 0 when the step size goes to 0. So this is essentially the same definition. So we are going to keep this and start talking about higher order methods. So the question, section 3, can we do better? Of course we can. And if you think about what we are doing when using the Euler method, we're using just an evaluation of the vector field at a given point to predict the next one. So we are using instantaneous information of the equation or the trajectory, just the derivative of the trajectory at a given point. So ways to improve that. Well, take intermediate evaluations. If I want to go from time t0 to time t1, I can try to have some information from time, for instance, t1 half or t1 3, something between t0 and t1. That's a way to improve. I mean, using more information than Euler is using. Second way to improve, use previously computed values. So now, if with the Euler method, I start at x0, then I predict x1, and immediately I throw x0 to the garbage. I may be writing down in a file the x0, but I'm not using it anymore in the computation. So I could keep x0, and with the help of x0 and x1 try to do something better to compute x2, the next step. So that's another idea. I say this. Sorry. I would say that the first point is looking into the future somehow, and the second point is looking into the past, the previous points computed. And then there is a third way, which is use higher order derivatives. So I'm using just the first derivative of the trajectory, which is f, the vector field. I could use more, and that's another point of way of proceeding. This should be, in this analogy, look better where you are. Look better at the present. So let's start with intermediate evaluations. And this is the approach of Runge-Kutta methods, which are maybe the very best known methods to solve ODE. And the formulation has to do with the weak form of the Cauchy problem. So I look at the ODE as an integral. And okay, I have a very good methods to solve or to compute numerically integrals or quadratures. So I try to use one to compute this integral. So as there are many methods to do quadratures, well, you have to fix one. And the usual method is the Gaussian quadrature. I mean, for the formulation of Runge-Kutta methods. So the Gaussian quadrature makes use of this this kind of approach in which you want to compute an integral and then you put some weights and you have a fast method to compute the integral, right? So I won't enter into details, but just notice that here we have an integral. This omega is some weight function, and then I approximate it with some sum, which are values of the function I'm trying to compute the integral, and some weights. These weights and the grid I'm evaluating the function depend on the weight function, omega, and then probably the initial condition. I mean, the initial and the final condition, A and B. But the point is that do not depend on the function I'm trying to integrate. So if we do this and we apply it to the weak problem or to the weak formulation, we can do some algebra and then do a change of variables and put the step size here. And put the step size here. And yes, I have something which is close to an stepper for an ODE. I mean, this is similar to the Euler method. I would like to make you notice. It's similar, but instead of having the vector field, I have an integral here. An integral. Okay, so I use this Gaussian quadrature, and I end up with something like this. I mean, I'm using the method, and I get the sum with the weights, the evaluations of the functions at some time steps, which, by the way, I do not know. So the quantities in which I am evaluating the vector field are not known. Okay. So the idea here, and I won't enter into details again, is that we use linear combinations of the vector field, similar to the one step of Euler, to approximate these quantities. Okay. So where I end up to the general formulation of the Runge-Kutta methods, which, I mean, they're kind of a cumbersome. This is the general formulation, a sum, which is, I mean, again, similar to Euler, because instead of having f here, we have a weird term, depending on some b's and some k's. The k's are these linear combinations of the vector field, okay? And the b's are some weights, some weights. And we have complete freedom, not complete, but we have freedom to choose both the c's and the linear combinations, which are given by a matrix, and the weights as well. So we have as many as Runge-Kutta methods as you want. I mean, that's the thing. There are certain things when you impose that this has to solve the equation that have, I mean, that are fixed. For instance, the sum of the weight has to be equal to 1. That's a requirement. And then we have standard choices to to comply with things like consistency and on non-trivial convergence, that basically makes you this selection. But apart from that, notice that we have many freedom, and in particular, we have the freedom of the number of terms, this S. This is called the stages, or the number of stages of a Runge-Kutta. Okay, in principle, one should think that as the more stages I have, the better order I have, or the better method. Okay, but the number of stages has to do on how many terms I put when solving the integral. So it should be better, but it is not always better. So the order of an Runge-Kutta method is smaller than the number of stages I choose. At least if the number of stages is large enough. Okay, so this is a standard way to present Runge-Kutta methods, which are by means of the so-called Butcher tableau. And of course, you have methods of many stages and many orders. By the way, Euler method is a Runge-Kutta method of one stage, the simplest, the only one, in principle. Here we have a method of two stages, which is called Heun's. And this method has order 2. And it is not the only method of two stages. There are more. In fact, there's a continuous parametric family of methods. But essentially, here this column here indicates the grid. The thing below inside indicates the coefficients of the linear combination, the matrix. If there is nothing, it means that it is equal to 0. Okay, and these b's here are the weights. So this determines a Runge-Kutta method. This is another method, due Heun's, but this time it has 3 stages and order 3. And this is the OG. I mean, this is the classical Runge-Kutta method of order 4 stages. And this is, I mean, when someone says the Runge-Kutta method, is probably referring to this one, even though there are much better methods than this one out there. So, as I said, in general, it's not true that S stages means order S. And there are theorems to prove that. So first of all, something I said, the error, by the way, the error is always smaller than, this is a mistake. The error is always smaller than the number of stages. Sorry. The error is smaller, that's a theorem. And then if the number of stages is, if I want to fix a method of order 5 or larger, I need strictly a value of stages which is strictly larger than 5. So I cannot achieve a Runge-Kutta method of order 5 with 5 stages. And then the problems keeps going as I do if I require more and more precision or more and more order. Sorry. So for p equal or larger than 7, I need at least 2 more stages than the order required. And if p is equal to 8, I need the number of stages to be at least p plus 2. So these 2 theorems, which says is that if I want Runge-Kuttas of higher and higher order, I will have to work a lot, because these tables have to be done with many rows, and the coefficients have to be computed, and these coefficients are obtained by using, solving equations, and that's a mess. So here I have a table with the minimal number of steps to obtain a Runge-Kutta of order whatever, 1, 2, 3, 4, up to 8. And as you see at the beginning, you can, that's Euler, 1, 1. And you can go on 2 stages order 2, 3 stages order 3, 4 stages order 4. But then for order 5, you need 6 stages. For order 6, you need 7. For order 7, you need 9. For order 8, you need 11. And the largest methods I've seen of Runge-Kutta are of order 10. And they have like 17 and 18 stages. So that's a lot. I mean, that's a mess to work with. Long set of coefficients. So this is the test equation I've used before. And then I'm using here 3 different methods. The good old friend Euler method, which is that here. And then I have a Heun's method, a Runge-Kutta 2, which is the green line. And then I have the classic RK4, so the classic Runge-Kutta of order 4. And I would like to make you notice that these methods are overperforming here. I mean, the error here at the beginning is less than what I should expect, because the step size is 10 to the minus 6. So, and this guy is going to more or less the accuracy I have in double precision, 10 to the minus 16. So, this is because the solution is very simple. It's a parabola. And I'm kind of, the methods kind of interpolate the parabola with more points than the one that are required. To interpolate a parabola, you need 3 points. So, but however, that's a side comment. We see behavior as expected as we keep integrating. Okay. So, again, when we want to do, in fact, a real computation with a real problem, we need to estimate the error, the local error. So, and this is done again to control the step size, as we did with Euler. Generally, with the Euler method, we only had one method, and that's all. That's the only thing we had. But if we have a whole set of methods, which are the Runge-Kutta family, which are many of them, I can think of using 2 methods to estimate the error. One, it's going to be the stepper, and the other one will be just to check how, will be the simulator of the true solution to check how much error I'm doing. So the idea, and that's also true for other methods. We use a couple of methods, and one is of larger order than the other, and this other one with higher order is the one as regarded as the true solution. Okay, and with that we estimate the error. So what we do with Runge-Kutta methods, the orders here are in principle arbitrary, just one larger than the other. But the Runge-Kutta methods have a very particular approach because of, you want to minimize the computational effort. So you cannot say, I'm going to use a method of order 25 and another method of order 50 to estimate the error. That's impractical. So we have Fehlberg's approach, and this Fehlberg's approach was developed, in the Apollo program to go to the moon. That's something from the 60s, And here I found a technical report for NASA. I mean, that's on the internet. You can read it, but I do not recommend it because it's a technical report. I mean, there's a lot of formulas and yeah, the deduction of many methods. So the idea of Fehlberg is the following one. I'm going to use, here is the butcher tableau, but I'm not writing down explicitly all the coefficients. I'm using vector and matrix notation. So I'm going to use two methods, the CA B prime, which is going to be one method, for instance, Runge-Kutta 4, the one I showed before. And then I'm going to use another method of order p plus 1, if the first one is order p, the other method is order p plus 1, but the idea is that C, A, p tilde is the other method. So these two methods share the matrix and the mesh, A and C. Both methods have the same. So to compute the second one, which is of higher order, you practically need the same computational effort. So you can estimate the error you do almost for free. And that's the idea of Fehlberg. So this difference is used to estimate the error. And sorry. And you go like this. A side comment is that if you're using the Runge-Kutta method to solve an integral, so the vector field has no dependence on x, which is, I mean, is completely madness. No one will do that. But the estimations of error of the Runge-Kutta method are 0. So these guys here, if there is a quadrature, the problem is a quadrature, an integral, the estimation of error of the Runge-Kutta-Fehlberg method is 0. And that may be important and catastrophic at some cases. I'm going to enter into that. So with the Runge-Kutta-Fehlberg method, I can design a method which has an adaptive step size. So I can control the step size. And the idea to control the step size is the same one as in the Euler method I presented before. But instead of using the half step to estimate the error, I'm using a method which is of higher order, p and p plus 1. This is why when you go to internet and look for some Runge-Kutta method, you see the Runge-Kutta method 7.8 or the 4.5, ODE 4.5 in MATLAB. 4.5, first of all, is referring to the number to the order of the method you use to predict, and the method you use to estimate the error. That's the meaning of all these packages in MATLAB and so on. And let me say that to do this, the only price you have to pay is to use more stages, probably in the lower order method, because the matrix have to be the same. So your requirement and the number of stages are the minimal requirements for the highest order. So if the order is p plus 1 and is 8, you need the number of stages for order 8. Also for the first scheme, let's say. So I mean, the idea of the step size is exactly the same, but here the estimation is done according to the order we're using. I mean, and this factor here is changed according of the method. If it is order p, is order p. Okay, and in principle, by the way, one could use to do the prediction, one could use both the prediction given by the lowest order method or the highest order. I mean, Fehlberg advised use the prediction by the lower method because it's the prediction you're sure the error you're committing, let's say, because you're estimating that error. But in principle, the prediction by the highest order, the order +1, is better. So you can use the other one. So I think that's Feldberg had some philosophical reason to choose the lowest order. Okay. Let's move to linear multi-step methods. I'll try to be very fast on this. I even have examples because the idea is practically the same as the I mean, not the same, but very similar to the one of Runge-Kuta's, which is but instead of using the steps forward, you're using the steps you already computed, your values of the solution you already computed. And this is originally proposed by Bashford and Adams. If you've used linear multi-step methods, you've probably heard about Adams-Bashford method and other Marshall-Bashford prediction correction schemes and so on. So there's a whole family of methods that come from the ideas of Adams and Bashford. So this is the idea, very simple. Let me notice that we have the prediction here we want to do, and then we are doing a stepper, very similar than the one like Euler. This is M plus S. And here we have, again, some evaluations or some linear combination of evaluations of the vector field. The only new thing here is that this depends on values that are already computed. This depends on previous values. Okay, so that's the idea. And yeah, the only thing is that we have some weights here, and we have to choose them in order to get the better method as possible. And then these are constructed in a very similar way as Runge-Kutta does, in the sense that you take the weak formulation of the Cauchy problem, and then you do some dirty trick or some method to compute this integral. I will remember that in the case of Runge-Kutta methods, you use the Gauss-Legendre method, quadrature. And here, since you have some points already on the integral you want to compute, because you already compute the previous points, what you do is interpolate the points. And instead of integrating the vector field, you integrate a polynomial, which is much easier. And this polynomial is an interpolation of the points you already have. And you make that work, adjusting with orders and Taylor expansion and so on. That's the idea. And in principle, the great achievement of these methods is that each time you do a one step, you need just an extra computation, evaluation of the vector field, because the other one requires you already computed that. So that's very efficient. Notice that with a Runge-Kutta method, you have to, compute whatever the number of stages, you have to evaluate the vector field at each stage. So here you have it once. But the world is not that simple. And we will see a little problem on this. But in principle, this was a very good idea. So no one should be surprised at this point. The first Adams method, which is Euler. If you don't use previous information, which is one stage, you get Euler method. And then this is for s equal to 2. And notice that this is kind of an Euler iteration with some weight. And then you use the next step for evaluation. You get x x plus 1, xn, x plus 1, and you get x plus 2. So that's a two stages method. And we could go on and compute in the weight and so on. But I'll put the an order 3 method, which, I mean, it has this kind of shape. Notice that, again, I would like to stress this. If I want to compute x plus 3, these two guys, these two evaluations of the vector field are already computed from the previous steps. The only problem maybe if how to start, because at the beginning you have just the initial condition. So you don't have 2 points previously computed. But then you can, usually what you do is you start with the Euler method, and then you can use this guy here, the second, the method of 2 stages to compute the next one, and keep going on, and you end up with a method of 5 stages or whatever, and then you keep using these last 5 points for the rest of the computation. So this happens. What didn't happen to the Runge-Kutta methods, it happens for the Adam-Bachelor methods. It means that if it has S stages, it has order S. So that's another advantage, maybe. But the error estimation and this, not the error estimation, the step size control for Adam-Bachelor methods is a pain in the ass. This is called Mille device. The word device to refer to a step size control should warn you already. I mean, and the ideas are practically the same. You use a couple of methods, one of order P and the other one of order P plus 1 or whatever. Sorry, you use 2 methods of the same order. That's another strategy for the control. So you use steppers of the same order, and then one of them is implicit. And this will be discussed later, what an implicit method is. But one of them behaves better than the other. That's the point. And the one which is explicit is used only for error estimation. So you use the prediction of the implicit method. But the point here is that when you want to adjust the step size, you have to remesh again. So you cannot any longer rely on previously computed points. You have to do a remesh to make the things work. And that's the main flaw of this kind of methods. That the step size control is no longer nice. You have to compute again all you have to evaluate again the vector field, which is the more expensive thing in all the integration. So, third method. I've just done looking at the future, looking at the past, and then I'm going to do the looking better at to the present thing, which is the Taylor method. The Taylor method is very simple. Again, the idea behind is even more simple than the previous one, because you take the differential equation and make a derivative with respect to the time at both sides of the equation. So you have to apply obviously you assume that x is a function of t, and you have to apply the chain rule and so on, and you end up like with a thing like this. So x dot and expression like this, which depend on the derivative of the vector field, essentially, here and here. Okay, and we have x dot. So we could use this already to improve Euler method, because with this I could compute the Taylor expansion of the solution given the first term is f, if is the vector field, times h, and the second term is this guy here, which is more cumbersome, times h squared. So I have already the Taylor expansion of the solution up to order 2. But the idea is not to stop there. The idea is to keep doing derivatives. I'm not doing a third derivative here because I wouldn't have enough space. I mean, that can be done. Up to third derivative is doable already, but the idea is I keep derivating and I'll try to compute all the derivatives of the solution by power matching. So I end up with a tremendously cumbersome expression in which, to compute the derivative of order n of the solution, I need the derivatives of order n minus 1 and minus 2 of the solution, and then all the derivatives as well of the vector field. Okay? So as something similar like this to this, but with any order. So I have some sort of recurrence, and I can work with that. And the recurrence is very, very easy. Is something like this. Okay? But I mean, this is very simple. This is the normalized derivative. This is standard notation. Normalized derivative is the derivative of order whatever divided by the factorial that appears in the Taylor expansion. But this guy here is a little monster because comes from a composition of functions. So this guy here is this guy here in order 2. So that's the hard part of Taylor method, and the reason, I mean, computing this is the reason that in most of undergraduate courses they don't teach Taylor method, because I mean, in terms of coding, that's a little bit hard. So we construct the Taylor polynomial, computing these derivatives by any means. And then we have the next point of the solution. So that be x1. So I have x1. And notice that here I mean, there is a change of paradigm because the order is as large as you want. I mean, and it can be adapted at each step. So now I have, I mean, if I expand to order n, the derivative, I get an order n method, but then I get x1 from this, and I do again the expansion again on x1, and I get, I mean, I can stop at any order I want. So if for n, for x0, I need order n, and if for x1, I need order n plus 2, I can do it. And the increase in computational cost is not so much. So this is, I mean, this is basically, this is quite different. Because at each point of the prediction, we expand the Taylor series of the solution up to any order, and then use that to predict. And notice that the step size here can be huge if the solution, I mean, huge in terms, I mean, taking into account that's then a step size. So that should be something small. But I mean, if I have many derivatives, I can get a lot of precision. So this thing here, which is the hard part in terms of coding, the thing you don't know how to do, this is done not by hand, of course. I guess many of you have had thought about that. You don't do it by hand. This is not done neither with a computer using numerical differentiation, It's not using the classical formulas for numerical differentiation, nor, and it is not done using symbolic differentiation. So this method cannot work with, using Mathematica to to make the symbolic derivatives of the function and then somehow use this. I mean, it can be done, of course, but you cannot go to high order. You cannot go to order 60 doing this using Mathematica. So you do the third thing is to use automatic differentiation, which is some sort of middle term or middle ground between numerical differentiation and symbolic, because it is symbolic in the sense that the computation is exact, so you don't add errors as you do in the numerical differentiation, but it's exact up to the operations you do, which are sums and products. I mean, you have the truncation errors because you're doing it in a computer. And then you basically, what you do is to cast your standard double precision arithmetic by an arithmetic of polynomials. And but that's cumbersome. Hopefully there is a software package which is public. I'll give the reference at the end. That can be used. I mean, it provides you the Taylor method, and you don't have to do nothing about that. But if you want to code it by yourself, you have to be very, very good at coding, let's say. So a couple of things about the Taylor method is that the step size, let's say, can be computed as, there is an optimal step size and an optimal order, and the step size optimal, you only have to estimate the radius of convergence of the series, and this is very easy. I mean, you have to look at the last term of the series and use the square root criterion or whatever. So that's very, very nice to know easily the optimal step size. And the optimal order is linear with the number of digits of accuracy. See, if I want to double the number of digits of accuracy, I have to double the number of digits I have to double the order. So that's, this has no competition in this world of finite order methods. Think of going with a Runge-Kutta method from, let's say, accuracy, tolerance, 10 to the minus 10 to double, 10 to the minus 20. How small I have to do the step size? Massively. It's impracticable. And here, the only thing I have to do is Taylor expand up to order 20 or whatever. I have to double the order. So there is no competition with Taylor when you go to high precision. And that, at least if you don't have weird things in going on. So this is the summary of Taylor method, and basically the take-home message here from the Taylor method is that if you can use it, because at least if you want high accuracy, it's the best one. If you want something fast, you may rely on Runge-Kutta methods. Okay, so these are the three versions of ways to improving the Euler method. Here we have a comparison. Again, I'm using the test of conservation of momentum, of angular momentum for the Kepler problem, and I'm integrating here 1,000 unit of time and checking for the log 10 of the difference between the angular momentum. And I'm using two integrators which are fantastic. One is Euler. Sorry, not. One is Runge-Kutta-Feldberg 7, 8. So order 7 and 8, and the step size control strategy by Feldberg. And the other one, which is the purple one, is Taylor. And I don't know the order nor the step size of, the step size, I don't know it because it's variable for both. And Taylor has also variable order. So Taylor does a little bit better than Runge-Kutta method, but I would like to stress that both do it fantastically. The energy drift here is 10 to the minus 13. So good enough. That's almost no error. So, yeah? Yeah?
It depends, for example, on the number of variables, on the CR1 that you already said, or for example, on the type of dynamical system. So autonomous, if there are periodic orbits, if the constraints logical factors, so
yeah. For strange for chaotic dynamics, that's a thing. That depends on what you want to do, essentially. This answer I leave it for the end of the talk. Okay. Then essentially Runge-Kutta method can be faster than Taylor because it requires less effort. But Runge-Kutta methods are worst in terms of accuracy, but are very good. So the answer here, which is not very sophisticated, is that if Runge-Kutta methods are good enough, and you require to do a lot of integrations, use Runge-Kutta method, and it doesn't matter if the system is autonomous or non-autonomous. There are things that matter regarding the dynamics of the ODE, and we'll see some things now. But in principle, if you want to relax and be sure of the accuracy, I will use Taylor because it's very fast as well. Take into account that it can do long step size, larger than any Runge-Kutta for instance. So you're fast because of this, because you have to do less steps, and then you have less accumulation of error because you have less steps. So in practical, I use Taylor method, and if I have to do a massive simulation, which I require something to be fast and maybe fix the step size, I use a Runge-Kutta. That's so. I'm going the other way around. Cripples, bastards, and broken things. This is a catchy title, I know. Do you want to do a photo? Yeah? Okay. Okay. So that's a phenomenology that basically breaks down the methods I've just presented to you. And the first one is very, very well known. I'm sure I'm sure Philip will know about this more than me, which is stiffness, which is a phenomenon that's ubiquitous, for instance, when solving partial differential equations. So an equation can be stiff, and I'm going to explain you now what a stiff equation is. But essentially, if an equation is stiff, it's going to kill all the methods I've explained this afternoon. None of them will be useful because they are explicit, all of them. So what an stiff equation is, this can be understood with a linear equation. Imagine then we have a linear equation with whatever the initial condition is. And we look at the eigenvalues of the whole spectrum of the matrix, and do a change of variables to put everything in the diagonal form. So I look at the diagonalized system. So this is a diagonal system, which means that the equations are uncoupled. So I have a set of whatever the number 1D equations. So I have a number of one-dimensional equations, and I'm going to suppose that there exists an eigenvalue which is negative and large in modulus. So minus lambda, and lambda is larger than 1, and think of something big in modulus. So this is a trivial equation. I mean, this is linear one-dimensional equation, so the solution is the exponential. X to the x of t, x to the, x, the exponential of minus lambda t. So if lambda is a large number, if it's a large positive number, this goes to 0, I mean, very, very fast. So there is not much interest on this solution in the sense that it's going to 0 fast, and that's all. Gets stick to 0. So let's see what happens if we apply an Euler method to this. We apply an Euler method. The equation is very simple, so I can work out the things and compute an expression for the nth step of Euler method. Basically, we have this xn plus squared, xn, h lambda xn, but then xn is given by xn minus 1. So you do a recurrence like this, and you take a common factor, and then this is something like xn equals to this factor here to the n times x0, and here x0 is 1. I mean, that's the initial condition, doesn't matter for the argument. So so this is what you get, and notice that, I mean, I want to approximate something that goes to 0 very, very fast, and I have this thing. This thing, if 1 plus h lambda is larger than 1, it blows up. So it's not only going to 0, but it's going to infinity. So you essentially need this guy here inside to be smaller than 1. And okay, if lambda is big, you're in trouble, because of course h, which is the step size, has to be smaller than 2 over lambda, and if lambda is big, h has to be very, very small. So your method is going to be very, very, very slow, because it has to do small step sizes. This is the stiffness. This is the stiffness, and the reason basically why there exist implicit methods. Okay, so I keep going. Just a side comment, there is something called the domain of stability of a method, and this is essentially constructed with these, for Euler methods. I mean, it's constructed with this equation, and you basically want to h minus h times lambda to be smaller than 1. So if I say minus h times lambda is z, then I have this equation. Okay, so that's an abstract, if you want, and z is complex. That's an abstract way to look at this phenomenon, and you have a region of the complex plane in which the system can converge. So that's the domain of stability of the Euler method. Now, here I present the implicit Euler method, which is the only implicit method I am showing today. And basically, the difference here is that this guy here, I want to predict x n plus 1, and I have to evaluate the vector field at the n plus 1, x plus 1. So I have to solve an equation. And that's the standard thing on implicit method. To predict, you do the stepper, but you need as an extra step to solve an equation. So I apply this to the very same equation, the linear equation x dot equal to minus lambda, and then I get a similar expression, and I compute again the nth iteration. So I end up with something like this. And notice that this is the x0 if you want, this one. And this converts for any positive step size and positive lambda. I mean, lambda is positive from the beginning. Okay. And if you define the domain of stability of the implicit Euler method, you have real part negative of z. If you remember that z is minus h lambda. Okay. So you have a nice domain of stability for the implicit Euler method. And this is in fact what you use to define the stability of a method. So the domain of stability can be generalized for any other method. You can do this kind of things. It's harder, but you can do as well. Compute the domain of stability for Runge-Kutta methods, for linear multi-steps methods, and check for that. And a system, a method is called A-stable if the domain of stability of the implicit Euler method is contained in the domain of stability of the method. So it contains the half left part of the complex plane. So that's the stability. Is someone talking? Okay. A stability, there is G stability and more letters than I can remember. So, I mean, there is a stability defined in terms of nonlinear equations, let's say, but this is the classical one. By the way, no explicit Runge-Kutta is stable. So they don't work for stiff equations. But for any order, there exists an implicit Runge-Kutta method that is stable. So we can solve stiff equations with implicit Runge-Kutta methods of any order. I mean, desired. In particular, you have all the Runge-Kuttas that you have of order whatever for explicit method. You have them in its implicit version. But in the case of linear multi-step methods, the highest order of an A-stable multi-step method, which has to be implicit, is 2. That's called Dalkey's second barrier. So the best, if you want to solve an stiff equation with a linear multi-step method, you'll get order 2. It doesn't matter what method you pick. But that seems it's not good enough. I mean, compared with Runge-Kutta. But there are reasons. I mean, people is using linear multi-step for stiff equations, and they do it for reasons. I mean, there are reasons to do that. And of course, there is an implicit version of Taylor that, I mean, is long step sizes, any order, and so on. So same situation as with explicit methods, but of course, if the Taylor method is hard to code in its explicit version, in its implicit is way harder. And I don't know of a public software domain that is available now. So more common that does implicit Taylor methods. So bad luck. So a remark on implicit methods is that they are able to cope with stiff equations, but they are, heavier than the usual methods, explicit methods. So they are meant to deal with stiff equations. And if your equation is not stiff, you shouldn't be using an implicit method because it performs worst. It's heavier because you have to solve an extra equation. So there is no point if your equation is not stiff, because implicit methods are more expensive. So do not use implicit methods just in case there is a stiffness. Okay. And if you can, you should know whether an equation is stiff or not. A feature of Taylor method is that most of all the explicit methods fail to handle stiff equations. Some of them, Taylor is no exception, but Taylor can detect that an equation is stiff. So it fails, but it knows why. And the reason is very, very simple, which is if you look at the series expansion of this solution of this linear equation, one-dimensional, which is this guy here, you have a large, I've put here 10 to the minus 10 to the 4. You have a large lambda, which is competing with an factorial. Now, the factorial is going to win. That's for sure. But if lambda is large, it may take a while for the factorial to win. Yeah? You need to compute a big factorial. So in the Taylor series of stiff solutions, you can observe behaviors like this. Again, I'm showing the logarithm, the 10 logarithm of the norm, the absolute value of each Taylor coefficient. And you can see that goes, a little bit larger than 10 to the 15. That's large. So it grows a lot. And then at some point, the factorial wins, and this decreases quite fast. This goes to 10 to the minus 20, and this happens for the first 16 Taylor coefficients. So this can be detected when you have the whole, or at least the 16 first digits of the Taylor series. So Taylor method will tell you, I'm failing because of this, because the equation is stiff, if you look at the coefficients. Okay. By the way, this stiff direction is the bastard of this section. Another bastard is this equation, which is very, very, very simple. Okay. This is an equation cooked out by Angel Jorba last week to show this phenomenon I'm going to use. And it's an equation cooked out for the sine of t to be the solution. If you put here sine of t and substitute, this is the solution. And notice that there is an autonomous part, which is alpha times x, and a non-autonomous part, meaning that if alpha is 0, this is a quadrature. This is an integral. Do you remember when I presented the Runge-Coulter-Feldberg strategy? I said if you use the Runge-Coulter-Feldberg strategy with an integral, you'll have problems. Then here there are the problems. I'm gonna pick alpha, not 0, of course, but 10 to the minus 4. 10 to the minus 4 is small, but not 0, clearly, but quite small. So I'm not doing a quadrature, but I'm doing something which is close numerically. And since I already know the solution, I'm going to integrate time to p, so t to pi, and then I should get 0. Right? So I use a Runge-Coulter-Feldberg asking for accuracy 10 to the minus 12, and I get this. I get a fail. I get this. Not 0, but 10 to the minus 7. I'm demanding 10 to the minus 12 of accuracy. So I lost 5 digits. Integrating an equation which is trivial, not very complicated, one-dimensional. And this is because this is close to a quadrature. So if I used the strategy of step size by Werner, which is another alternative stretch size very similar to Fellberg's, but it manages this small error, I get 10 to the minus 16, which is what I should expect. I mean, something small. So be aware of using Fellberg's strategy or Runge-Kutta-Fellberg for problems that can be like this. And be like this is not that hard. I mean, if you have an equilibrium point and something perturbed with something which is periodic, you are in this situation because an equilibrium point, the vector field is 0. So close to is small. And you have some perturbation which is purely time dependent. So that's not that weird. More monsters. Yeah. The difference is that I mean, to explain briefly, is that you pick up different methods. I mean, these weights, these. So the problem you have that the predictions are the error prediction is 0 when the vector field doesn't depend on x, doesn't happen. So you change a little bit the coefficients. So this is another funny thing that if you integrate a very simple Hamiltonian model, which is a standard linear oscillator, okay, and you use Euler method, this in principle, I mean, this has an equation form. This is a Hamiltonian, and this quantity should be conserved, but it's not generally due to propagation of error, and that's something which is a thing. I mean, people is scared about this because there is, I mean, all the methods tend to gain energy or lose it depending on the method. And this is the reason why there are symplectic methods, which are methods built up specifically to preserve energy. Okay, this is just a situation, a very simple situation. I use an Euler method, which I integrate for a long time. I mean, that's 20 units of time. And I mean, in the phase space, it goes away because it's gaining energy. And if I check the Hamiltonian, it goes up. I'm using a very large step size to make the things happen fast. I mean, I'm doing the things bad on purpose, but it's okay. It would happen the same if I use a smaller step size. And this is a very nice phenomenon that this is Euler method, which is a Runge-Kutta order 2. I would try a Runge-Kutta order 4, Euler method is order 1. If I tried a Runge-Kutta of order 2, and instead of winning energy, I'd lose for this example. And if I try order 3, I gain energy again, a Runge-Kutta of order 3. And if I try order 4, I lose energy. So it depends on the parity of the order of Runge-Kutta, whether if I win energy or not, or lose it. But that's a funny thing. So the reason why there exist symplectic integrators is this. But be aware of symplectic integrators, because there are phenomenon that, I mean, happens behind your step size. I mean, there are monsters living under your step size. And this is a region, I mean, this is the face portrait of a standard map. I don't mean to explain what's this, but this is complicated pattern dynamics. And in particular, there is chaos. This is a model for Hamiltonian chaos, in fact. So very, very pathologic dynamics. And this is the formulation, very, very, very simple. In fact, it's so simple that it is a one symplectic Euler step of the pendulum. So the pendulum, which is the simplest mechanical, I don't know if the simplest, but very, very easy. It's integrable, it's fantastic. It has essentially periodic orbits, equilibrium points, and periodic orbits that do infinitely many turns. I mean, it has essentially a very small set of behaviors which are simple. And if I try to simulate the pendulum with this, here I got, I mean, I picked up an H 0.5, which is large on purpose to see the bad behavior. But I mean, as long as H is different from 0, you'll have chaotic motion and it's bounded by H. So H0, you have no chaotic motion, and then you have a little bit of chaotic motion if H is small. And as H increases, you see this kind of behavior. So there are monsters living under the step size. And this creates artifacts. And I think I've seen artifacts published in papers. I mean, there are simulations that I do not believe. And I think this, I mean, they get in chaotic Hamiltonian dynamics because of this kind of phenomenon. But that's just, I'm just suspicious. So this was just a philosophical example, if you want. Let me go back. Because, I mean, in all the methods, we're using, if you want, discrete time dynamical systems to approximate a continuous one. That's what we do. And as you know from this course, they are very, very different. I mean, discrete time dynamical systems can have much more involved or need less dimensions to have involved phenomenon happening. You need only one dimension with maps to have chaos. With ODEs, you need 3. So, in particular, with 2 dimensions, you cannot have a 1 degree of freedom Hamiltonian system, so 2 dimensions. With chaos, and you can have the standard map, which is 2D symplectic, time discrete, and have plenty of chaos. So be aware. And the last thing is that why we can't predict the weather. That will be something fast, I hope. And the reason is chaos, chaotic behavior. So I'm going to answer the question by Josep from some minutes ago, if I remember it. So this is the so-called Lorentz system, which is a model for atmospheric convection, madly simplified model. I mean, this has not quantitative meaning, but a lot of qualitative meaning. This was the rediscovery of chaos. I mean, it happened with this model. And let me say that, I mean, Josep can tell you the story if you pay him a beer or something. Okay. So the reason is we have a 3-dimensional model, ODE, and it has some parameters. And then if you picked the right selection of parameters, which is, I mean, there is an open set of that, but for instance, this selection of parameters, you have a strange chaotic attractor, which is dominating the dynamics. And this I mean, this is an integration of an initial condition okay, which is this one. And so this is a trajectory. But the trajectory is attracted by this by this object that you can, I mean, it is drawn by the trajectory. This object is strange in the sense that it's something between a surface, a surface and a 3D object. It has fractal dimension. I mean, it is a little bit more than a surface. It has fractal dimension of about 2.06. And it is chaotic. And we'll see what chaotic means now. By the way, this is a couple of Poincare sections. So I'm cutting this at Z25. So I'm cutting this here. And I'm looking at the points that this object crosses this value of Z, and putting in purple points the ones corresponding with crossing with negative velocity of Z dot, and in green points I'm putting the ones that cross with positive velocity. So there are two Poincare maps here, and this is, they say that I mean, this is strange, and you can see it, but because you're cutting this Poincare section and you have something which resembles a curve. So the geometry is not trivial. And then let me do a numerical experiment. I'm going to use the very same initial condition as before, 1, 0, 0. And then I'm going to use this and this, a perturbation, which is a perturbation of 10 to the minus 8 in one direction, in direction X, and 0 in the others. So these two initial conditions are so close we cannot detect it like in this plot. I'm going to propagate this model with a Taylor method, which is fantastic, very, very good accuracy. And I found that this. In principle here, both equations start at, both initial conditions start at the same point. I'm putting one in blue, the other one in yellow, so you cannot distinguish them. But as long as you integrate, this goes like this, and you end up like seeing two different trajectories. They are separated. So you can measure how separated they are with respect to the time. And you see this kind of behavior. So for 10 units of time, you get more or less the same error you started with, 10 to the minus 8, okay? 20 units of time, you get more or less the same. 30 units of time, you get 10 to the minus 4. I mean this is the error doing I mean the computation, subtracting and computing the norm, and this is the first variational equation. I mean, this is just to show that the error can be computed with quite good accuracy, computing the variational equation or solving the variational equation. So up to order 30, you have already lost 4 digits. I mean, order 30, no, 30 units of time. 10 to the minus 1 for 40 units of time. And in 50, which is not much, you've lost all the digits. So this is what you get, two completely different solutions or trajectories. Okay, so let me say that I'm doing the things correctly. I'm using a very, very good integrator that performs well, that is accurate, it's fast. And in 50 units of time, I'm losing all the information. That's because there is sensitivity with respect to initial conditions. So I can do nothing about to cope with this phenomenon. I can do one thing. Since I'm losing digits, I can use more digits to try to solve this effect. But at some point, I will lose this race. I can use 200 digits, and then I will be able to predict a longer time, because I'll be losing a lot of digits, but I'll have enough. But at some point, I will lose the race against chaos. That's the reason we cannot predict the weather. Because if this happens with this very simplified model, I mean, I don't know if you can imagine what happens with the realistic models for convection and pressure and so on for the weather models. So don't be harsh on people that do weather forecast, because they do what they can do. So with this, I'm done. Just let me do some show you some references. These are three classic books of ODEs, method for ODEs. These two, the Norset, Heider, and the Serles, are kind of a thought for mathematically trained people. So they have a lot of tricky things to show. And then the best book I know to start is the Butcher's one. So I will start with this one. And then this is a paper in which they explain you this software package that provides you with a Taylor integrator for any equation. So you can use that. It's public software. And there is a paper explaining how it is implemented and so on. So you can check the paper and use the package, because it is very good. So I'm done. Thank you for coming. I don't know if I have to check the chat. There are questions?
I have a
I
question.
answered your question, Josep. Okay. So what was the question? The question was what happens if you have a strange chaotic attractor? Yeah.
So if you have criteria to choose between Jorba or Taylor, because I just explained the Jorba is not good when the Taylor is
yeah. Yeah. Yeah, I think I mean it is an attractor. So the attractor, I mean, if you want the envelope, the attractor works for you. I mean, you could use Euler. I mean, if you want the attractor, because it is massive, it is doing the work for you. It is very easy to, I mean, compute an attractor is trivial. It does the work for you, the attractor. Now, if you want to predict, I mean, an initial condition where you will be from some time to time, I mean, you have to do this. Track the error due to the chaotic behavior, whether with the variational equation or the Lyapunov exponent, whatever. I mean, this is just straightforward. Okay. And then at some point you will notice that you cannot believe what you're, I mean, you cannot believe the predictive capacity of your method. So then the only thing you have to do is to use more digits. So the answer is use Taylor, because if you have to use more digits, use Taylor, which is better than a Runge-Kutta method of fixed order. But if you want just to do a picture of the attractor, and I mean, do whatever you want, and that'd be reasonable. Okay. There is someone in the chat talking.
Yes.
Yeah.
Can you hear me?
Yeah.
It's not an advanced question. I just don't really remember. Can you recall why Runge-Kutta method fail when the differential equation only depends on time? I don't.
Yeah.
You mean
It fails because it's close to an equation which does not depend on x. So the equation is f of xt, and the dependency on x is very small. So it is essentially an integral, a quadrature. So you're using the Runge-Kutta method to compute something which is an integral. And the hypothesis for the Fehlberg step size control in that kind of systems fail. I mean, fail or are close to fail. They require the derivative of the vector field with respect to x to be different from 0, but if it is small, since you're doing numerics, you're having troubles. And the troubles are that you're losing a lot of digits in a small time integration.
okay?
Yeah?
Thank you. Thank you. Yes. Thanks.
Welcome. Yeah. Hmm?
And well, in which kind of application or situations in two steps you get a really high accuracy, like so in that situation that you use like really high floating point.
No, I wouldn't use. I mean, I use Runge-Kutta of order. I used 8, 9, I think here. I mentioned order 10, but because I know they exist, never used order 10, but they are quite high in order. And I've used this kind of integrators in long integrations in the solar system. Okay, because you have, I mean, you want to do as many. I mean, if you want to integrate 1 million years, the solar system, for instance, you want to do as many very few step size as the smallest number as possible. That's the situation I've used it. But you can use, I mean, to compute periodic orbits in a quite simple system, polynomial system. I mean, if you build up a lot of code depending on your integrations, the better they are, the best situation you are. I mean, there are periodic orbits that they are unstable, and that propagates error in the same way that this does it. This strange attractor. So you are interested in relying on better integrators.
So concerning the fitness,
Yeah. Mm-hmm. Yeah.
Are there any general way to know if it's steep or how much steep? Way to know it?
This is the way. Oops. This is the way. I know. Man, I'm not. I mean, I don't claim that there are no many others, but in principle, I mean, you can use your approximate. I mean, your stepper, your Runge-Kutta stepper to build up an approximation of the Taylor expansion. I mean, you can do that. It's hard as hell, but you can do that. But this kind of thing is what you can measure easily, let's say, in a code in an automatic way. So I'm saying that the Taylor packets by Angel, Jorba, and Maurosong are, I mean, it does not this. I mean, it doesn't tell you that the equation is stiff, but in the next release, it will. So it will tell you the step size is too small, and it's because or I cannot continue, so on, and that's because the equation is stiff. They are putting that in the software.
But then you have a
Yeah.
smaller step size like 10 to the power of -7. Right?
Yeah.
Then if it's very, very steep, the program will not work because it will get stuck there.
Well, if it is very, very stiff, it may happen that it is very, very stiff that it diverges. But if not, of course, you can do it. I mean, depending on how stiff the equation is. But you're using a very, very small step size. So it will take a while to integrate maybe something that with an implicit method will be a few seconds.
But the idea is that with the erratic step size, this round of error that you are doing when h is very small, then you are compensating in jumps that are larger.
Well, the idea of adaptive step size is that you can rely on the estimates of local error. I mean, that the local error behaves as you expect because the step size is small enough. And that's, if you want, affects everything, affects local and global error. So, because you're doing at each step less error. Okay. So, if there are no more questions, it's been a pleasure. Thank you.